You're lying in bed right now. Maybe it's late. The blanket's pulled up to your chin. The room is exactly the temperature you like it. You reach for your phone, scroll for a second, and a song comes on. Maybe it's one you haven't heard in years. And before the chorus even hits, you feel it. A wave. It starts somewhere at the back of your neck, rolls down your arms, and suddenly every tiny hair on your body is standing straight up. Your skin looks like the surface of a plucked chicken. Goosebumps. You didn't choose that. You didn't flex a muscle. You didn't think, I'd like my arm hair to stand at attention now, please. Your body just did it. Without asking, without permission. And here's the thing that should bother you. That reaction, that weird, involuntary, bumpy skin thing also happens when you're freezing cold. It happens when you're terrified. It happens when someone tells you a story so beautiful you can't speak. Cold, fear, beauty. Three completely different experiences. One identical physical response. So the question is actually simple. Why does your body do the exact same thing when you hear a piece of music as it does when you're about to die? What is your skin trying to tell you? And why, after millions of years of evolution, does a reaction that seems completely useless still fire every single time? The answer takes you back about 2 million years, and it changes the way you think about your own body.
Let's start with what's actually happening under your skin, because most people have never thought about it. Right now, attached to every single hair on your body, there's a microscopic muscle. It's called the erector pili. It's so small you'd need a microscope to see it, and you have millions of them. Each one wraps around the base of a hair follicle like a tiny fist gripping a flagpole. When that muscle contracts, it yanks the hair upright and pulls the skin around it into a little mound. That mound is the bump. That's the goosebump. It's not your hair doing something weird. It's a muscle, one you can't control, physically pulling your skin into a new shape. And the signal to contract doesn't come from your brain. Not the thinking part anyway. It comes from your sympathetic nervous system. The ancient automatic wiring that handles everything you don't consciously decide. Heartbeat, breathing, digestion, fight or flight. The same system that dumps adrenaline into your blood when a car swerves toward you is the system that gives you goosebumps when someone plays Claire de Lune. Think about that for a second. Your body classifies a Debussy composition and a near-death experience in the same neurological category. But here's what nobody tells you. This reaction wasn't built for you. It was built for someone with a lot more hair. About 1.5 to 2 million years ago, your ancestors looked very different. Homo erectus was walking upright across the East African savanna, and their bodies were covered, fully covered, in thick, coarse hair. Not like a gorilla, not quite, but far closer to a chimpanzee than to you. Every arm, every leg, every inch of torso was insulated with fur, dense enough to trap air. And that's exactly what goosebumps were designed for. When the temperature dropped, the sympathetic nervous system fired. Every erector pili muscle contracted at once, and millions of hairs stood straight up. This created a thicker layer of trapped air against the skin. Air is an extraordinary insulator. That puffed up layer of fur acted like a biological blanket, holding body heat in, keeping cold out. No fire, no clothing, no shelter, just hair standing on end, keeping your ancestor alive for one more freezing night on the open grassland. You can still see this working perfectly in animals today. A cat in winter, a goose in the cold. Watch a chimpanzee when the temperature drops at the Gombe Stream Research Center in Tanzania. The hair rises, the body insulates. The system works exactly as designed. But insulation was only half the job. Here's the part nobody talks about. Picture your ancestor maybe 800,000 years ago. It's dusk. She's walking back toward her group, and something moves in the tall grass. Something big. She doesn't know if it's a predator. She doesn't have time to find out. But before she can even process the fear consciously, her body has already responded. Adrenaline floods her bloodstream. Her heart rate spikes, her pupils dilate, and every hair on her body stands straight up. This wasn't a glitch. This was a weapon. When an animal covered in thick fur puffs up, it looks bigger, substantially bigger. And in the calculus of predator versus prey, size matters enormously. A hyena approaching a lone hominid that suddenly appears 20% larger has to recalculate the risk. Is this thing actually bigger than I thought? Is it worth the fight? Porcupines still use this exact strategy. Their quills are modified hairs, and when threatened, they erect every single one, transforming from a shuffling ball of spines into something that makes even a pride of lions at Londolozi Game Reserve in South Africa back away. Male Nyala antelopes raise the white fringe along their backs during dominance displays, making themselves appear massive to rivals. Cats arch their backs and puff their tails for exactly the same reason. Your goosebumps? Same system, same muscles, same nerve pathway, same evolutionary logic. The only problem is that somewhere along the way, you lost the one thing that made it work. The timeline of human hair loss is one of the most debated puzzles in evolutionary biology, and the honest answer is that nobody knows exactly when it happened. But the evidence points to a window between 1.2 million and 200,000 years ago. Tina Lasisi, a biological anthropologist at the University of Southern California who specializes in the science of hair and skin, puts it this way: we technically still have hair all over our bodies. It's just miniaturized to the point where it functionally doesn't insulate us anymore. You have roughly the same number of hair follicles per square centimeter as a chimpanzee, about 60 per square centimeter, according to research published in the Indian Journal of Dermatology. The follicles are still there. The hairs they produce are just tiny, wispy, almost invisible. Vellus hairs, scientists call them. Ghost hairs, basically. The leading theory for why this happened is thermoregulation. As your ancestors moved out of the forests and onto the open savannas of equatorial Africa, they started walking longer distances, then running. Persistence hunting, chasing prey for hours across open ground until the animal collapsed from heat exhaustion, may have been one of humanity's first great survival strategies. But running in the equatorial sun with a full coat of fur would have been catastrophic. Overheating would have killed them faster than any predator. So the fur thinned, and something extraordinary replaced it: sweating. Humans became the most prolific sweaters in the entire animal kingdom. You have between 2 and 4 million sweat glands across your body. A horse sweats, a dog pants. But nothing on earth can cool itself as efficiently as a naked, sweating human being running in open air. Mark Pagel, a professor of evolutionary biology at the University of Reading, has also proposed that parasites played a role. Ticks, lice, biting flies, they all evolved to live in fur, to lay their eggs in fur, to feed through fur. A hairless human was a parasite-resistant human. And in a world where a single infected tick bite could kill you, that mattered enormously. Either way, the result was the same. Your ancestors traded their fur for sweat glands and parasite resistance. But evolution is slow, and it doesn't clean up after itself. The erector pili muscles stayed, the nerve connections stayed, the entire goosebump system remained perfectly intact, wired and ready, like an alarm system in a building that no longer exists. So that explains the cold, that explains the fear, but it doesn't explain the strangest goosebumps of all, the ones you get from music, from a speech, from watching your kid take their first steps, from a sentence in a book that hits you so hard you have to put it down and stare at the wall. This is where it gets genuinely fascinating. In 2016, Matthew Sachs, then a PhD student at Harvard University, published a study that changed how neuroscientists think about this. He put people who regularly get goosebumps from music into a brain scanner, and he compared their brains to people who don't. What he found was structural. People who get chills from music have a physically denser network of nerve fibers all connecting their auditory cortex, the part of the brain that processes sound, to the regions that process emotion, particularly the insula in the medial prefrontal cortex. More fibers, more connections, more efficient communication between hearing and feeling. In other words, for some people, the bridge between I hear this and I feel this is a highway. For others, it's a dirt road. And when that highway carries enough signal, when the music is unexpected enough, Beautiful enough, perfectly timed. The emotional processing centers light up so intensely that they trigger the sympathetic nervous system. The same system, the same ancient fight or flight wiring, the same erector pili muscles. Your body doesn't distinguish between a lion is coming and this chord progression is devastating. The intensity is what matters. The signal strength. When emotion crosses a certain threshold, your body reacts the only way it knows how. It fires the old system, the one built for fur that no longer exists. A 2024 paper published in the journal PLOS 1 by Felix Scholler explored this further, describing these responses as aesthetic chills, and found they're closely linked to dopamine release in the brain's reward pathways, the same chemical that fires when you eat, when you fall in love, when you win something. Goosebumps from beauty are neurochemically a reward signal. Your brain is telling you, pay attention, this matters, this is significant. But here's perhaps the most remarkable twist of all, and it was discovered only recently. In 2020, Yachie Su, a professor of stem cell and regenerative biology at Harvard University, published a study in the journal Cell that fundamentally reframed what goosebumps actually are. Her team found that the same system that causes goosebumps, the sympathetic nerve connected to the erector pili muscle connected to the hair follicle, is also a stem cell regulation system. The nerve doesn't just make the muscle contract, it communicates directly with hair follicle stem cells. Under normal conditions, the low-level activity of the sympathetic nerve keeps these stem cells in a poised state, ready, waiting, primed for action. But under prolonged cold, when the nerve fires at higher intensity for longer periods, it doesn't just cause goosebumps. It activates those stem cells. It triggers them to regenerate the hair follicle, to grow new hair. Chu's team showed this in mice, and the implications are staggering. Goosebumps aren't a useless leftover. They're the short-term response of a system whose long-term function is hair regeneration. The quick muscle contraction is the emergency setting. The sustained nerve activation is the rebuild setting. Same wiring, two different timescales. Your goosebumps are your body trying to grow fur that your genes no longer allow it to produce. Think about that for a second. Every time you step outside into cold air and feel that familiar ripple across your arms, your body is attempting something it lost the ability to complete over 1 million years ago. The signal fires, the muscles contract, the stem cells receive the message, and then, nothing happens. Because the blueprint for thick insulating fur was edited out of your genome somewhere on the African savanna, probably around the time your ancestors started running down antelope in the midday sun. The machinery is still running. The factory just doesn't make that product anymore. So let's pull all of this together, because when you line up everything goosebumps actually are, the picture that emerges is extraordinary. Your body inherited a system that served at least 3 critical survival functions for your ancestors. It was a thermostat, contracting millions of tiny muscles to trap insulating air against the skin when temperatures dropped. It was armor, puffing up a coat of fur to make your ancestor look larger, more dangerous, harder to attack. And it was, as Harvard discovered in 2020, a regeneration trigger, a direct line from the nervous system to the stem cells that grow new hair, ensuring that the coat of fur your ancestor depended on was always being repaired, always being renewed. Cold came at your ancestors like a slow killer, and the goosebump system answered with insulation. Predators came at them with teeth, and the system answered with size. Damage came at their fur, and the system answered with regrowth. 3 threats, 1 elegant machine, and then evolution did something it almost never does. It removed the output, metum, the thick fur, but left the entire machine running. 2 million years later, you're sitting in a dark room with headphones on. A cello hits a note you weren't expecting. The dopamine fires. The sympathetic nerve activates. The erector pili muscles contract. The stem cells receive a signal they can no longer fully act on. And your arm breaks out in tiny, useless, beautiful bumps. You are, in that moment, experiencing a 2 million-year-old survival system misfiring in the most human way possible. Not because you're cold, not because you're in danger, but because something was so beautiful that your body confused it with both. So the next time you feel that wave roll up the back of your neck, when a song hits, when a story lands, when someone you love says exactly the right thing at exactly the right moment, look down at your arm. Those tiny bumps are not a malfunction. They are a message from the deepest, oldest part of you, a part that still remembers what it was like to have fur, a part that still thinks, after all this time, that it can protect you.